Hello students, welcome to this lecture in which we're going to start talking about triple integrals. So what is the story with the triple integrals? Suppose we have an expression in three variables. W equals f of x, y, and z. Defined at all points on and inside a rectangular parallelepiped that has sides parallel to the coordinate planes. So what we have to know that we can't visualize four-dimensional space, unfortunately. So what we can consider? We can consider that we can consider the four-dimensional volume, described in this problem. So we will think the same way as in 2D and 3D. So basically our thinking will be that we can chop the rectangular solid into many subrectangular solids. Then we can choose arbitrary points. We could choose arbitrary points inside, in each of them, and we usually put stars on these arbitrary points. So x sub I star, y sub I star, z sub I star. Then we could calculate So let's try. So it's going to be f of x sub I star, y sub I star, z sub I star. So basically this is like the same logic as before, multiplied by the volume of this subrectangular solid. For I, j, and k, right? For I, j, and k. So basically what we're going to get is f of x sub I star, y sub I star, z sub I star times delta x sub I, delta y sub j, and delta z sub k. Right, so we take all of the dimensions of this little solid and multiply them together to get the approximation. So that means we can calculate chunk of volume, which is dv equals to delta x, delta y, delta z. Then we can add all of these pieces up. So we could find the Riemann sum. Basically the sum over all I, j, and k of f of x sub I star, y sub I star, z, I said I, right? So this should be mistake, sorry. This should be j, this should be k, sorry. I made a small mistake, should be j, it should be k. Right, so small mistake here, right? Z sub k star times delta x sub I, delta y sub j, and delta z sub k. Then we're going to consider v to be the limit when the norm of the partition goes to 0 of the sum over I, j, and k, of this of this sum, right? So f of x sub I star, y sub j star, z sub k star times delta x sub I, delta y sub j, and delta z sub k. So basically this is a triple limit of a triple sum. So finally our volume will be defined as a triple integral over this region f, x, y, and z, and this is a chunk of volume dv, right? Or we can think of it as triple integral, the first one from a to b, c to d, and e to g of f of x, y, and z, dx, dy, dz. So what is a reasonable question to ask? The question is, what kind of functions can be integrated? What kind of functions w equal to x, y, and z inside of f can be integrated? That's the question that we can ask. So basically, we can say that if f of x, y, and z continues except at few points, right? It might be discontinuous, perhaps at finitely many points, right? Except maybe finitely many points on and inside the rectangular solid. It's pretty much the same as before. So if it's discontinuous at just few points, it's fine, but if it's in infinitely many discontinuities, you can't really integrate. All right, so let's look at the example. So in this example, so example, so in this example we want to find the volume of the parallelepiped bounded by x between 1 and 3, y between 2 and 4, and z between 5 and 8. So basically we have to calculate hypervolume under w equals to 1 to get volume of a box. So we have integral 1 times dx dy dz, and our limits go from 1 to 3, from 2 to 4, and from 5 through 8. All right, so let's start. So we have two integrals left, 2 to 4, 5 to 8. If we integrate 1, and integrating 1 will get x from 1 through 3 dy dz. So if we move forward, we get integral from 2 to 4, 5 to 8, and we plug in 3, so it's going to be minus 1, 3 minus 1, so we're going to get 2. So we have the integral from 5 to 8 of 2y evaluated from 2 to 4 dz. So we have the integral from 5 to 8, 5 to 8, and we plug in 4, so it's going to be 8 minus 4 dz. So if we integrate the answer from 5 to 8 of 4 dz, we're going to get 4z evaluated from 5 to 8. Alright, so we plug in 8, so we're going to get 4 times 8 minus 4 times 5. So 32 minus 20, so we're going to get 12. We're going to get 12. So what about the next example? Next example is our region is x is between 0 and 1, y is between 0 and 2, and z is between 0 and 3. And our function w is in x, y, and z equal to x, y squared, z cubed. So we get the v equal to integral from 0 to 3, integral from 0 to 2 for y, and integral from 0 to 1 for x, and we have x, y squared, z cubed, dx, dy, dz. So let's start calculating it. So we still have two integrals left, and then we integrate x. So x will be x squared over 2, x squared over 2, we have y squared, we have z cubed, and we evaluate it from 0 to 1, dy, dz. So we still have two integrals left, 0 to 3 and 0 to 2. So we plug in 1, it's going to be 1 over 2, and when we plug in 0, we're going to get 0. So it's going to be 1 over 2, y squared, z cubed, dy, dz. So now we only have one integral left from 0 to 3, and antiderivative of y squared will be y cubed over 3, and we can take 1/2 and put it outside probably. So we'll have y cubed over 3, then we'll have z cubed evaluated from 0 to 2 dz. So we have 1/2, one integral from 0 to 3. So when we plug in 2, we're going to get 8 over 3, and when we're going to plug in 0, it zeroes out, so that's what we're left with. So if we take constants and put them outside, 8 divided by 2 would be 4. So we'll have 4 over 3 integral from 0 to 3 of z cubed dz. So we have 4 over 3 z to the 4 over 4 evaluated from 0 to 3. Finally, when we plug in 3, we're going to get 3 to the 4 over 3 minus 0, so it's going to be 27. And that's our answer for this problem. Alright, so in the last example for this topic will be the following example. So in this example we need to calculate the following triple integral. Integral from 0 to 1, integral from 0 to x, and integral from 0 to ln of ln of y, ln of y, and the function is e to the x plus y plus z dz dy dx. So the order is switched around. Alright, so let's try to do that. So we're gonna get two integrals left, from 0 to 1, from 0 to x, and we integrate the e function, so it's just gonna be e itself, so it's e to the x plus y plus z evaluated from 0 to ln of y, and we have dy dx left, So let's plug it in. So what do we get? We get integral from 0 to 1, integral from 0 to x. So we plug in ln first, so we're going to get e to the x plus y plus ln of y minus e to the x plus y if we plug in 0, dy dx. Alright, so we're going to write this expression as two parts. So we're going to write it, and we did something similar in class. So we have 0 to 1, 0 to x. So we'll have x e to the x plus y, e to the ln of y minus e to the x plus y dy dx. And e to the ln of y is just y, so we're going to get integral from 0 to 1, integral from 0 to x, e to the x plus y times y minus e to the x plus y dy dx. Alright, and so now we can factor the common factor. This is a common factor, so we have integral from 0 to 1, integral from 0 to x, e to the x plus y times, and if we factor the e, then it's going to be y minus 1 dy dx. Alright. So we need to calculate this integral, which is not really easy to do, so we're going to do the integration by parts. So we'll say that e to the x plus y, we'll do it on the side, y minus 1 dy. So we'll think of u as y minus 1. We're going to think of u prime as 1, and v will be e to the x plus y, right? Then v prime is also e to the x plus y. So integration by parts tells you that u times v, so it's y minus 1 times e to the x plus y minus the integral of e to the x plus y times dy. Alright, so we get y minus 1 e to the x plus y minus e to the x plus y, which is y minus 2 e to the x plus y if we again factor the common factor, and so it's going to be y minus 1 minus another 1, so it's negative 2 here. So that means we've done this integral separately, so we can just plug it into this expression over here. So we can say equals integral, only one integral left, from 0 to 1, and we have what? We have what do we have? We have y minus 2 e to the x plus y evaluated from 0 to x, from 0 to x to x, sorry, dx. So we plug in x first, so we're going to get the integral from 0 to 1, x minus 2, y to the 2x, and then when we plug in 0, we're going to get minus 2 e to the x. Sorry, here it's a mistake, should be e. E to the 2x, e to the x, dx. All right, so we calculate so this one is easy to calculate because it's e to the x, but here we have to use the same logic as we just used, right? So that means what? That means if we think of u to be x minus 2, then the derivative of u is 1. And if we think of v dv as if we think of dv as e to the 2x, then v would be the integral of e to the 2x, which is e to the 2x over 2, right? All right, so what does it tell us? This tells us that our integral is equal to the integral from 0 to 1 x minus 2 e to the 2x dx plus the integral from 0 to 1 of e to the x times 2 dx. And for this one we use the integration by parts. So by part, this integral x minus 2 e to the 2x dx becomes u times v, which is x minus 2 times v, right? So it's e to the 2x over 2 minus the integral of v du, right? So e to the 2x dx, and the integral of e to the 2x dx is just so it's going to be x minus 2 e to the 2x over 2 minus e to the 2x over 2, right? I'm sorry, made a small mistake here. Should be over 2 because that's a v, right? V should be over here, so it should be over 4. So we take this and we plug it in over here for this integral. So we have x minus 2 times e to the 2x over 2 minus e to the 2x over 4 plus this 2, and this is e to the x evaluated from 0 to 1. All right. I think we did it right, so we plug in 1, so it's going to be negative e to the 2x over 2 minus, so we plug in 1, sorry, this is just going to be squared, right? E squared, then minus e squared over 4 plus 2e. When we plugged in 1, then we put a minus, and then we plug in 0. So if we plug in 0, we're going to get negative 2, 1 over 2 minus 1 over 4 plus 2. Okay. So let's continue on. So we have e squared over 2 minus e squared over 4. Right, so it's going to be 3 of them. So negative 3 e squared over 4 plus 2e. Then this 2 and 2 goes away. We have so minus 1 plus 2 is 1. 1 minus a quarter is going to be 3/4 with a minus. So that's our long integral. Alright, probably a good place to stop this lecture, and I'll see you in the next one.